So next, let's look at a very similar pattern to the 0-1 knapsack. This one's called the Unbounded Knapsack. This one is so similar that we'll be spending some of this video reviewing the basics that we talked about earlier. Even the problem is actually almost exactly the same. But in my experience, the Unbounded Knapsack is more common when it comes to interviews, so it's very important to learn. Also, these types of dynamic programming patterns are so complicated that I think as much practice as you can get is really helpful. Also, we'll be going deeper into how to actually think about this type of problem and how to approach it, and a bit on why this algorithm works in the first place, which I don't think we got a chance to discuss with 0-1 knapsack, even though that lesson was quite long already. So once again, we're given a list of items and a backpack with some limited capacity. These are our items, of course. This item has a profit of 4, a weight of 5. Again, we're trying to maximize the total profit that can be contained in our backpack that has a fixed capacity. But in this case, we actually have an unlimited quantity of each item. So originally, when we got to the first item, we had a choice. We either include that item or we don't include that item. Originally, our capacity is 8. If we include that item, our capacity becomes 5. If we don't include that item, we skip it, our capacity stays 8. So far, this is exactly the same as the 0-1 knapsack, but here's where it's going to change. This side is going to stay the same. When we skip the first item, we're going to assume that we're never going to use it again. We're only going to use the next 3 items. We're going to go to the second item. We have a choice of whether we include it or not. Actually, I think our capacity over here was actually going to be 3 if we choose the first item. But over here, when we choose the second item, our capacity decreases by 2 because that's the weight of the item. So when we choose that item, we have a weight of 6 left. We have a capacity of 6 left. If we don't include it, we'll have a capacity of 8 left. Over here, though, what do you think is the decision? We chose the first item. So now what's our choice here? Are we choosing to include the second item or not? Well, if we did, then this would be exactly like the 0-1 knapsack. Is that okay? Not quite. Well, there's actually multiple ways to make this decision tree that's valid. I'll show you the other way, but I prefer this more simple way to do it. But there is a different way, and you can kind of choose the one that you prefer. But over here, we chose the first item. Now we have a choice. Do we want to choose that item again? Or now are we going to finally choose to skip that item and possibly move on to the next item? So here we have that choice. We're going to choose the first item again. What's going to happen when we do that? Well, it has a weight of 5, so then our capacity will be -2. We know, of course, that this is not valid. We should not be able to choose the first item multiple times because we get a negative capacity. So we basically don't go down this path anymore. Here, though, we basically choose, okay, finally, we're not going to be including this item anymore. We're not necessarily choosing this item yet. We're just moving to the next position here. So our capacity would stay the exact same. It would stay 3. And I'm going to go one level deeper just to show you the idea behind this, but I encourage you to draw out the entire decision tree. It helps kind of reinforce the ideas that we're learning here. So at here, we're now at the second position. And actually, you could even draw this decision tree keeping track of, what position we're at, because we know when we call this recursive function, those are the 2 variables that are going to be changing. What's our remaining capacity? And also, what index are we at? Initially, we start at index equals 0. Here, we stayed at index equals 0. We're still at the first item. Here, we went to index equals 1 and continued going like that. But when we're here, we can either choose this item or not choose that item. And also, the total profit that we would have gotten from each of these would have been 4 here, 0 here, 4 here, but we were not allowed to do that. 0 here. Here we chose the second item, which had a profit of 4 as well. So we got a 4 here. Here we skipped it. We got 0. So here we're going to choose the second item. It will leave us with a capacity of 1 because that item has a weight of 2. Here we would choose to not include that item. Our capacity would stay 3. Here we chose the second item, right? That's why we have a capacity of 6 remaining. We chose this item. Now we have a choice to include it again because remember, each of these items, we have an unlimited quantity of them. So we can just keep choosing this item if we want to, if that's what's going to maximize our total profit. So here we'll have a capacity of 4 remaining. This is not a bad item because its weight is pretty small and the profit is pretty large. But we could also skip that item and, choose, okay, we've had enough of this guy. We're now going to start selecting some of these. Skipping it would not actually change our capacity though. It would leave us with 6 capacity here. We chose to skip the first and second item. So we are at the third item. We can choose to include that item or skip that item. It would leave us with a capacity of 5 if we chose it, a capacity of 8 if we skip it. So the profit we would have gotten here from the second item would have been 4. Here we would have gotten 0. Here we would have gotten 4 again from that second item. Here 0. Here we would have gotten a profit of 7 because the weight was 3. And here we would gotten a profit of 0. So you're probably thinking that this is really, really similar to the 0-1 knapsack, and that's because it is. Actually, when we take a look at the code will only be like 1 or 2 lines different. The time complexity of the optimized DP solutions are also going to be the same actually, but for this brute force solution that we're doing, this decision tree, actually the time complexity is not going to be the same as the original, even though it kind of looks like we're having 2 branches every single time. And what's the height of the tree going to be? Maybe it's going to be n. That would make it 2 to the power of n. That's the same that we talked about last time, but it's actually not. The height of this tree is going to be potentially larger than n. Because with the 0-1 knapsack, for each item, we could have only chose that item a single time, or we could have skipped it. So for each level in our tree, we would have had at most 1 item. So the tree height would have been roughly n. But in this case, we can actually choose each item an unlimited number of times. To illustrate that, let's take a look at the last item we have. If we start with a capacity of 8, we choose the first item, we'll have a capacity of 7 remaining, and we can keep choosing that first item an unlimited number of times. The other branch would be maybe we skip that item and then we choose a different item. But going down that item with just a weight of 1, we would basically be able to keep choosing it until our capacity reached 0. So basically, in this case, the height would be the total capacity that we started with. Of course, this would only occur if we had an item with a weight of 1, but maybe we had an item with a weight of 2. In that case, the height of this tree would have been capacity divided by 2. We know we don't care about constants when we're talking about big O time complexity. So in this case, the overall size of the tree would be 2 to the power of c in the worst case. So that's what the time complexity would be. That's the size of our decision tree here. Now, before I jump into the code, I want to talk a bit about what are we doing here? Like conceptually, what is this? It's really abstract. We got numbers, we got choices, we got decision trees. There's a lot going on, and this is complicated. How can you reason about this on your own? Like, what's an easy way to think about this? Well, with dynamic programming, it's all about breaking a big problem into sub-problems. The original problem we were given, we have a capacity of 4, and we have these 4 items we can choose from, and we have an unlimited quantity of each of them. That was the original problem. That's the root node, essentially. And with this decision tree, we're trying to calculate all possibilities. And among those possibilities, we're trying to calculate the one that maximizes the profit, of course. When we go left here, we're trying all possibilities where we include at least 1 occurrence of the first item. That's what this left branch is. And then as we go further, we make another choice. When we go left here, we're saying we're getting all possibilities where we choose 2 occurrences of the first item. When we go right here, we said we chose 1 of these originally, but now we're done. We're basically, this right side here is going to be all possibilities where we only included a single occurrence of this first item, and then we stopped. We didn't choose any more, and then we started choosing some of the other items, essentially. So that's why this left subtree can give us all possibilities where we chose at least 1 of these, because this goes down the path where we choose more than 1, and this one goes down the path where we chose exactly 1. When we go right from our root, of course, we're choosing to not include any of these at all. We took this original problem and created a sub-problem where we said we're not going to include any of these. We were given 4 items, but now we only have 3, and we're fine with that. It's possible that the solution lies on this side of the tree, and that's what we're going to determine, whether it does or not. And as we go down this tree, we're going to further break this problem into more sub-problems. The left side over here is when we chose at least 1 of these guys. And the right side of this tree was when we chose none of these guys. So what we're saying is it's possible that the solution contains at least one of these. And it's possible that the solution actually contains none of these, and maybe the solution only contains these two items. So we keep breaking it up into subproblems until we've created all possible subproblems, and then we return the result. By the way, in this case, the solution will be going down the right path. We skip this guy, we choose one of these, so then we go left essentially, and we only chose one of them, so then we go right down our tree and start choosing a few of these. We choose exactly two of them. For the last item, we'll actually have 0 capacity left because our capacity will be 2 plus we chose 2 of these items, so plus 3 plus 3. Our remaining capacity at that point will be 0 because we already filled up our bag. And if we try to choose any more of these, we won't be able to. We will end up with a total profit, I believe, of 18 because we chose one of these and 2 of these. So it totals up to a profit of 18. So this is how I like to think about it. I think this is the simplest way to think about this decision tree in this the context of this problem. And it usually works for most unbounded knapsack problems, but I'll show you a slightly different template which also might work. We'll quickly go through that decision tree because it also does work, but I think the code can get a little bit more confusing because instead of having 2 branches, we actually have a loop of branches. We will once again start with a total capacity of 8. Yeah, right, this is our original problem, but instead of breaking it up into subproblems, we're just gonna go through every possibility out of every item that we can choose. So we're gonna have a branch for every item. If we choose the first item, we'll have a weight of 3 remaining. If we choose the second item, we'll have a capacity of 6. Sorry about that. I keep getting the capacity and weights confused. We can also choose the third item. We'll have a capacity of 5 left. If we choose the last item, we'll have a capacity of 7. So we're not actually skipping any of these, which maybe this is more intuitive for you. And then for each of these branches, actually, we're going to do the exact same thing. This is also one way to go through every single possibility. So here we would have 4 branches for every single item. So if we chose the first item, once again, we would get a negative capacity of -2 essentially. And we know this is invalid, so we would stop going down the tree at this point. We could choose the second item, which would leave us with a capacity of 1. We could choose the third item, which would leave us with a capacity of 0. And we could choose the fourth item, which would leave us with a capacity of 2. And for each of these, we would do the exact same thing, keeping track of the total profit. So if we chose the first item, would have given a profit of 4. Here we would have gotten a profit of 4, but we couldn't do that. Here we would have gotten a profit of 2 from the second item, here 3 from the third item, and here 1 from the last item. This might seem more straightforward to you conceptually, but coding this one up is actually a bit more complicated because we need a loop instead of just 2 cases. But it's up to you which one you prefer. I encourage you to try writing out this solution if you'd like. But now I'm going to be showing you the code of the first one that I talked about where we only have 2 branches every time. It's almost exactly the same as the 0-1 knapsack we showed last time. So here's the code. Now the time complexity is one of the things that changed. Instead of 2 to the power of n, it's 2 to the power of c, where c is the capacity. Other than that, it's almost exactly the same. Even if I had the other code over here, I bet you would be hard pressed to find the difference in this code because we are passed in the exact same variables. We have our DFS helper just like last time where we add a variable to keep track of which index we're currently at. The base case is where we, get out of bounds of the array, in which case we would return 0. We have still 2 choices. We can choose to skip the first item. If we skip it, we're going to simply call DFS on I+1, keeping the rest of these the same because that's our sub problem in this case. We're saying maybe this contains the solution. We can also choose to include the first item. That's our second path over here. And this is where we change things only slightly though. We calculate the new capacity if we, took the weight of this item. We want to make sure that we have enough capacity to even store this item in the first place. If we do, meaning our capacity is greater than or equal to 0, our remaining capacity is greater than or equal to 0, then we're going to include this item. We're going to take the profit of this item, add it with a recursive call to basically the exact same thing. This is the difference. Originally, for 0, 1 knapsack, we passed in I plus 1 over here because we knew that if we included the first item, we can't include it again, so we should pass in I plus 1 as the parameter. But this is where things are different with Unbounded Knapsack. We can keep including this item if we want to, as long as we have enough capacity. So we're passing in I here, but you do have to make sure to pass in the new capacity. That's the same as last time though. You pass in the new capacity. So this function call is not the exact same that we just made. Our capacity is the one value that changed here. So that's the sub problem. We started with a capacity of 8 and we had all 4 of these items. Now we have a capacity of 3, but we still have access to all 4 of these items. That's the idea. That's the one line that we changed here. Now, sometimes the difference between a 0, 1 knapsack and Unbounded Knapsack is more than just one line of code. So now when we take this and optimize it with memoization, just like we did before, where we cache each possibility that goes into this function. Remember, these two are always going to stay the same. These are essentially our arrays, but which element we're currently at and what's our remaining capacity is going to change. But we can actually apply caching to this just exactly like we did with 0, 1 knapsack. Let me show you the code for that. Even though the brute force solution had a worse time complexity, the memoization solution is actually going to have the exact same time complexity as the 0, 1 variation that we talked about, because the variables that we're passing in are the exact same. The ones that are changing, the capacity and I are the exact same. So all possibilities that we could pass in for I are from basically 0 to 3. So there's 4 possibilities in this example. All possibilities we could pass for capacity is 0 through 8. So roughly the capacity that we were given. So when we multiply those two together, we'll get like a 2-dimensional grid, 8 by 4, or I guess, 9 by 4 if you add that 0 here to 8. So this is our problem space. This is why when we apply caching to this, the natural next step for us is to go to the true solution, the true dynamic programming solution, because we know our solution space is a 2-dimensional grid. That's where all of our sub problems are going to lie. And the bottom right position of the grid is usually where the solution is going to be for the entire problem itself. But taking a look at this code, it's essentially exactly the same, where we do initialize that 2-dimensional grid. We have our recursive helper. We pass in 0 as the beginning index. We pass in the input arrays over here. We pass in the initial capacity, which is 8 for this problem. Also, we pass in the cache itself, the 2-dimensional grid. And once again, the only difference is going to be over here, where when we choose to include that item, instead of passing I plus 1, we just pass in I, because we know that we might be able to include this item multiple times. So now let's move on to the true dynamic programming solution. And this time I'm actually going to talk about a few of the things that we didn't get to talk about last time. Now, if all you care about is the code, this code is once again almost exactly the same as the original code. The difference being that over here, where we chose to once again include the item here, we can choose to include multiple copies of it. So here, when we take the profit of that item and then add to it the calculation of the sub problem is not being passed I plus 1. I plus 1 would mean now we have access to, some of the other items. But we're actually passing I because we might be able to include this item multiple times. Other than that, the solution is exactly the same, but I'm going to be talking about why this whole 2-dimensional approach works in the first place, because we didn't really get to talk about that last time. First of all, you might have noticed that I have items which keep track of the rows and capacity is the columns. Could we have done it the opposite way? Could we have rotated this grid 90 degrees and had capacity be the row and the items be the column? Well, we definitely could have, and it definitely would have worked for this solution where we actually have a 2-dimensional grid, and that's the time complexity and the memory complexity of what we're doing. But we also talked last time about how you can take this solution and optimize it with the memory at least. And the way we do that actually is instead of having the entire grid, we only keep track of at most 2 rows of the grid. We just keep track of the previous row that we calculated and the current row that we're currently calculating. because that's all we really need, because we saw that last time, in some cases, if we choose to skip this item, we'll have to go and calculate the max profit where we skip that item, but the capacity stays the exact same. That calculation is happening right over here, where in our two-dimensional grid, we go to the I-1 row. So essentially from this position, we end up going up one position. But also last time we saw that we actually end up going top left as well. We end up at most going to the I- row. That's when this line was changed. It was I-1, but we also ended up taking the current capacity that we're at and decrementing it, not just by 1, but by some variable number, which is the weight of the item that we're adding. So in that case, we saw previously we would go top left, though in this case, we don't have to go top left because our I in that case is going to stay the same. So in that case, we would just go to the left. But it still could be a variable amount. It's not just going to the left by 1. That would be pretty simple. It's going to the left multiple spaces. That's why I made this grid in this orientation, because with this, we only have to keep 2 rows in memory at a time. So I'm going to show you how we can take this solution and optimize it. This is also the reason why we take our grid and fill it from top left and then go to the right. And only after we've done this entire row, then we start computing the next row, because it might happen in some of these positions, we have to look up. How can we look up if we haven't even computed what goes above in the first place? And also why we go left to right. We might have to look left. How can we look left if we haven't computed those yet? We can't really go in this order. So that's why we're doing it this way. Also, I want to mention, actually, it is possible if you modify this solution to, instead of filling it from top left, filling it from bottom right and going left and doing it like that. Like, that's one variation sometimes I do, because this actually matches up more similarly to the memoization solution that we talked about. But in terms of code, I think most people prefer it this way, which is why I'm doing it this way. It makes more sense. The reason why we can do it in the opposite order, like from bottom right and then go up and go to the left, is because at the end of the day, this is a two-dimensional grid. It's symmetrical. So if you modified the code, you would be able to do it in the opposite way. When we do it from top left to bottom right, what we're doing here is saying, in this position, for example, if we only have access to this item, what's the max profit we could get when we have a capacity of 1? Okay, what's the max profit we could get with a capacity of 2, with 3, with 4? Well, with any of those capacities, we can't get a profit at all. We have 0 because the weight of the item is 5. But once we finally have a capacity of 5, we can include that item and we get a profit of 4. And we can keep including that item, but we can only include it one time, no matter how high our capacity gets, because our max capacity is 8. If our capacity got to 10, for example, we would be able to include 2 occurrences of that item. We'd have a profit of 8, but in this case, it doesn't do that. And then when we get to the next position over here, we have access to 2 items. We have access to the first item and the second item. What's the max profit we could get when we have that with just a capacity of 1? And then we ask what's the max we could get with a capacity of 2, with 3, with 4, etc., etc. I definitely encourage you to fill out this grid on your own for practice. But now I'm going to be moving on to the memory optimized dynamic programming solution. So with the most optimized solution, the time complexity is the same, but we save on memory. We only have to keep at most 2 rows in memory at a time. And ironically, as we keep getting more optimized solutions, it seems like we get less and less code. That doesn't mean that this solution is more simple to come up with, though. This time, we actually have a single row. We don't even have this two-dimensional grid. We just have a single row that's the size of the capacity plus 1. So we have like one of these rows, not even this row here, but pretend like we had one row over here and we fill it with all zeros. We use 0 as a default value essentially, because the next thing we're going to do is we're going to start going row by row for every single item that we have. So now our job is going to be to build the second row. We're going to create that. We're going to call it current row. It's going to be the same size. It's also going to be all zeros initially. we would go position by position, and we would say if we skip this position, if we skip this item, we're going to go to the previous row, which we called DP, and we would go to the same capacity that we had, and that would be our skip value. That's why we default this array to be all zeros, because the first value we want this to be is 0 if we skip the first item, because if we skip the first item, then we have no items available, and we would want the capacity to be, we would want the profit to be 0 in that case. And so we keep doing that, and we also do it for these positions where we finally had enough capacity. In that case, we would have gotten a value of 4 by including this item. Maybe we would have had a capacity of 10 here. In that case, we would have gotten to include 2 of these. Then the profit would have been 8. Because from here, we would have looked to the left and saw that even with a capacity of 5, we would be able to get an item. So we can say 4 plus the capacity we have 10 would give us, we would be able to include this item twice. Now, after we've calculated that row, we're going to assign that to DP now, and then we're going to go to the next iteration of the loop and create a new row down here, and it's going to be filled with all zeros. Notice how that first row is no longer in memory. We only have 2 rows in memory now. And we initialize these to all zeros, and then we start computing them. In this position, we have a capacity of 1. That's not enough to contain this item or this item. Here, we have a capacity of 2. That's enough to contain this item. So we have a profit of 4 here, still only that one item. Here, we can include this item. So we include the profit of that, but we also take in the current row, the capacity that we have, which is 4, minus the weight of including this item, which is 2. So basically that's us saying from this position, we're going to look 2 positions to the left and take that value and add it with the profit here. We would have also tried doing that from here as well, actually. We would have taken the profit, which is 2, added with the profit of the value 2 spaces to the left, but that value was 0. That tells us that with a capacity of 3, we can only include this item once. But when we're over here and we're looking 2 spots to the left, we can include this item twice with a capacity of 4. So here we get a profit of 8. And now just continuing to fill it out, and I encourage you to do this on your own. Here we would actually be able to do the same thing. We'd get a profit of 4 from including this item, and we'd look 2 spots to the left and see that we can get a max profit of 8. This is the sub problem that we already computed. Recursively, we would from here, recalculate this entire sub problem and then do all the work that it takes to compute that. But here with dynamic programming, we saved that result, so we don't have to solve that sub problem again. So here we would get a value of 12. I think here we'd also have 12. Here we would have gotten 16 actually, because we can get 4 of these guys. And then we would take this current row, assign it to DP, and then our current row would be the next row. And we would actually delete this from memory. This is no longer in memory because we only need at most 2 of these at a time, because we know as we compute the values here, we're only gonna have to look 1 row above. We don't have to look multiple rows above. And we'll maybe have to look to the left, but that's okay. So this is the idea behind the most optimal solution. I'll quickly run through the rest of this. With the third item, we can't include anything. With this, we can't include the third item, but we can include the second item. So we'd have a profit of 4. Here, we can include the third item. We'd get a profit of 7. Here, we can include the third item, but we can get a higher profit by including 2 of the previous item. Here, we can get a profit of 11 by including this item and including 1 of these items. Here, we can get a profit of 12 by including 3 of these items. Here, we can get a profit of 15, 1 of these, 2 of these, and here a profit of 16 by getting 4 of these. Here, we can get a profit of 1 because the last item actually only takes a capacity of 1. It takes a weight of 1. Here, it would have been 4, I believe. Here, we would be at 7. Here, we would be at 8. There's actually 2 ways to get this 8. We can get 2 of these, or we can get 1 of these and 1 of these. Here, I believe it's also 11. Here, I believe it's also 12. Actually, I just realized we had it wrong over here. We can actually get 14 over here because we can include 2 of these with a capacity of 6. So this, I believe, would also be 14. And actually, this position would be 18, I believe, because if we get 2 of these, that's 14, and we still have enough weight for this. So that would be 18. Sorry about that confusion. So this is 18. I believe with this, from here, we can choose to skip the last item, which is basically take the value above, or we can take the profit of this item, which is 1, plus the value to the left. Here we only go to the left by 1 because the weight of this item was 1. So what's higher, 15 or 14 plus 1? Well, they both equal 15. So 15 is going to go here. Here, we can either choose to get the value above, which is 18. We can take the max of that and take the max of this item if we choose to include this item, which is 1, plus the profit of the current row. The capacity we had was 8 minus the weight of this item, right? The ith item, which is going to be 7. So we basically look to the left. That's 15. So 1 plus 15 is 16. Which one of these two is higher? It's 18. So 18 is going to be our result. It's basically us taking 2 of these items and 1 of these. So this was a lot to get through, but I hope this is starting to make more and more sense to you. It definitely takes a lot of practice. I encourage practicing these problems on your own. Try writing out the table, try drawing out the decision tree. It helps a lot.